Following on from the previous video, we're going to talk about how to compute probabilities by conditioning. It actually works very similarly to expectation. Say we want the probability of A for some event A. If we can find the probability of A given x equals little x, which we can call some function g of x, for each value x, then we can actually define p of A given capital X as that same function g, but evaluated at big X. So that's allowing x to vary over the range of the random variable. Then we can find that the probability of A is just the expected value of this random variable, p of A given x. Remember, p of A given x is a random variable. It's a function of capital X, and we're going to take the expected value of that variable, and that will give us the unconditional probability of A. Essentially what we're doing is taking the probability of A for each value of x and then averaging those up over the possible values of x. So it works very similarly to double averaging. Depending on whether x is discrete or continuous, this will either be a sum of the conditional probability times the probability function or the probability density function dx if x is continuous. So essentially, this looks very similar, especially in the discrete case, to the law of total probability, or the partition rule. And essentially that's what it is. We're applying the partition rule here, where the partition is each of the different values that x can take on. And because it can be continuous or discrete, we end up with either a sum or an integral. So let's look at an example of doing that. Imagine that we have u is a uniform 0-1 random variable, and we're going to create a coin with a probability of heads equal to u. And we're going to flip that coin until we get a single heads and count up the number of flips that it takes to get that heads. And what I want is the expected value of x and the probability that x is greater than 2. See if you can think about how to approach this problem. What distributions are going on here? We definitely have a uniform 0-1, and we're doing something with the same probability until we get a single success. But note, x here, even though it sounds like it, is not geometric because the parameter, the probability of success, is unknown. It's this uniform random variable. But if we knew what it was, if we were able to condition on the value of that probability, then we would have a geometric. So essentially, the conditional random variable, x given u equals little u, is a geometric with parameter equal to u. So that x on its own is not geometric, but once we know u, it is. Okay, well that tells us a few things. First of all, it tells us that the expected value of x given u equals little u is 1 over u. And that means that the random variable e of x given u is 1 over big U. So again, we're just taking that function, 1 over little u, and replacing little u with a big U to turn it into a random variable. And we know that because geometric's mean is 1 over its parameter. So because of that, we can use double averaging to find the unconditional expectation of x as e of x given u. Well, that's e of 1 over u, and that's the integral of 1 over u f of u du. And notice if we have a uniform 0-1, that probability density function is just 1. That makes it really easy to integrate. So that gives us ln of u evaluated at 0 and 1. But that actually turns out to be infinity. The mean of this random variable does not exist. That integral diverges. That's kind of weird. So it's definitely not geometric because the mean doesn't exist. Similarly, if we're looking for the probability that x is greater than u, we can do the same thing. We can condition on u equals little u, and then we can find the probability. So that's going to be 1 minus the probability that x is equal to 1 given u is little u, and x is equal to 2. And because x given u equals little u is a geometric, we can just sub in the probability function. So we'll have u there, and then 1 minus u times u. And we can simplify that if we like. That's just actually 1 minus u squared. So that means p of x greater than 2 given u is that same function, but evaluated at big U instead of little u. So again, now this is the random variable rather than the value. And then finally, to find the unconditional probability, we just use double averaging. So the probability is the expected value of this probability conditioned on big U, which is the expected value of 1 minus u squared. You can get the integral and make sure you can evaluate this. It should give you 1/3. So this is kind of weird. We've ended up with a random variable x, which is pretty likely to be reasonably small, right? 2/3 of the time it's going to be less than or equal to 2. But its mean is actually infinity. The mean still diverges because there's just a chance that the probability of success is arbitrarily close to 0, and so a chance that x takes an arbitrarily long time to observe one single heads. This has actually got a name. A variable like this is known as a null proper random variable. So it has an infinite mean, but it has a guaranteed probability of being finite. Kind of weird. We'll see this idea again when we talk about Markov chains. Lastly, we're going to talk about computing variances by conditioning. If you remember from the very first video of chapter 3, if we have the random variable y given x equals x, it's a random variable, so it has a variance. And we would call it variance of y given x equals little x. We could write that, of course, as the expected value of y squared given x equals little x minus the conditional mean squared. So it's got the same definition as regular variance does. So that's going to be some function of x. And now we're going to define var of y given x to be the random variable that takes on the value of the conditional variance exactly when x takes on the value little x. So similarly to before, it's going to be a function of capital X. It will be k of big X instead of k of little x. So now we can find the law of total variance, or also known as the conditional variance formula. If we want the unconditional variance of y, we can take the expected value of var of y given x plus the variance of the expected value of y given x. So remember, those things inside the brackets, var of y given x and e of y given x, are both functions of x. So we're taking the expected value and variance of those variables with respect to x. And that seems pretty crazy, right? How is that possible that we can express the variance of y as the sum of these two components which are conditional on x? So I'm actually going to prove this. It's a pretty neat proof. So we'll split up the two parts. The first part is the expected value of variance of y given x. Well, we can sub in the definition of that random variable, var of y given x, and then we can apply linearity of expectation. So we'll end up with the e of y squared given x, and then minus e of that random variable e of y given x squared. So that squaring is happening inside the bracket. Okay. The second piece is the variance of the random variable e of y given x. And again, the definition of variance is the second moment minus the first moment squared. So that's going to be e of that variable squared minus e of y given x, and then squared on the outside. So now we're going to take those two things and add them together. E of var of y given x plus var of e of y given x. You'll notice that the second part of the first piece and the first part of the second piece are equal to each other, and they cancel out. So what we're left with is e of y squared given x minus e of y given x all squared on the outside. Well, by definition of double averaging, that first thing is just the expected value of y squared. And the second thing inside the brackets, that before we square it, is just e of y. So this just gives us the exact definition of the variance of y unconditionally. That's kind of cool. If we want to interpret it, that first piece represents the sort of variability of y for each value of x. And the second piece represents variability coming from x itself. And the sum of those two components both contribute to the overall variability of y. Let's look at an example. Imagine we're going to toss a fair coin until r heads appears, and we'll let n be the random variable that represents the number of tosses required. Then we're going to take a second coin that's biased with probability of heads equal to p and toss it capital N times, so whatever that was. And we'll let x be the number of heads that we get on that second coin. And I want to find the mean and variance of x. Give this a little bit of thought and think about what distributions are in play here. So that first coin, we're tossing it until r heads appears and calling that n. The second coin, we're going to toss it n times, where n is a random variable, and we'll let x be the number of heads on the second coin. So there's two different distributions at play here. And again, like before, x sounds binomial, but it's not quite binomial since n is a random variable. But if we condition on n equals little n, then we do have a binomial random variable. So that distinction is important. X on its own is not binomial because the parameter, the number of trials that we do, the number of times we toss that second coin, is random. But if we know that capital N is equal to little n, then x given n equals n is binomial. We also know that n itself is negative binomial with parameters r and 1/2. So that tells us that the expected value of n is 2r, and the variance actually also happens to be 2r. It's a coincidence that they're equal here. So now, if we want to find the expected value of x given n equals little n, it's the expected value of a binomial, so it's the product of the parameters, just n times p, which tells us that the random variable e of x given n is capital N times p. Same idea as before. We're taking our function np and replacing the little n with a big N because now this is the random variable. So that lets us, using double averaging, get the unconditional expectation of x as e of x given n. Well, that's just e of np, which we can pull the p outside. That's p times e of n, which is 2pr. Okay, that's for the mean. What about the variance? Again, because x given n equals little n is binomial, the variance of x given n equals little n is n times p times 1 minus p. And again, the random variable var of x given n is capital N times p times 1 minus p, just replacing that little n with a big N. So that lets us get the unconditional variance of x using that conditional variance formula. We have those two pieces that we're adding up. So we'll sub in our expressions there, np times 1 minus p for the first one and np for the second one. Then using linearity of expectation, we can pull the p and the 1 minus p outside. For the variance, when we pull the p outside, we have to square it. Don't forget that. And then finally, we can sub in the mean and the variance of n, each of which happen to be 2r. And if we like, we can simplify. That ends up giving us 2pr. I just want to note here, the variance and the mean were equal to each other, but that's not always going to be the case. It's just a coincidence for this particular example. I want to again outline the procedure that we've used for a lot of the examples in this video. Essentially, we know or we're given or we can find something about the conditional distribution. In this case, x given n equals little n. So then if we know the distribution, we can find the mean and variance. We can write it down or calculate it. Once we know those, we can sub in little n for a big N, and that gets us the random variables, e of x given n, and if we need it, var of x given n. And then we can use double averaging or the conditional variance formula, also known as the law of total expectation and the law of total variance, to find those values. So you're using both the information about one random variable condition on the other, as well as the unconditional information about n here. So that sort of technique is going to be useful. And again, in our next tutorial, you'll have a chance to practice this with several different examples. That's everything for this video. There's one more for this week about compound random variables, which uses all of these techniques again. Bye!